Okay, so good morning from India, everyone. It has been a wonderful conference. So today is the last day of the conference, and it's my honor to introduce the speakers. The first speaker is Professor Andrei Vesnin from Sobolev Institute of Mathematics and Novosibirsk State University, as well as Tom State University. He's going to speak about volume bounds with applications to a maximum volume conjecture. Over to you, Andrei.
Thank you very much. It's my pleasure and honor to give a talk here. And I see that our conference is very successful, and my pleasure to give a talk on the last day. So I would like to tell you something related to knot theory, but mostly related to hyperbolic point of view. So I would like to discuss hyperbolic properties of knots, particularly their volumes. And this is outline of my talk. Firstly, I recall you something about hyperbolic volumes. Next, I recall you something about Rye-Furrow invariants for free manifolds. And after that, we will discuss maximal volume conjecture and volume upper bounds. So talking about hyperbolic knots, we mean that we talk about knot complements as hyperbolic free manifolds. And at this point, I would like to recall you generalization theorem, conjectured by Thorson and proved by Perelman. In one of versions, this theorem states that the integral of every compact three-dimensional manifold has a canonical decomposition along spheres and torus in pieces which have model geometries, and by model geometries, we mean 8 Thornton geometries. Among them are 3 classical, Euclidean, spherical, and hyperbolic. There are 2 product geometries and 3 so-called exotic geometries related to Lie groups, nilpotent, solvable, and universal cover of acyl to R. And can you hear me?
Yes, we can hear you.
It seems there is some sound. Oh, okay, I continue. And most interesting is the hyperbolic geometry. So let me call something about it. Suppose why we interested in hyperbolic geometry? There are 2 reasons for us. Firstly, it's very rigid geometry, and secondly, a lot of knots admit hyperbolic structure. So by rigidity, we understand the following. So suppose we consider any dimensional hyperbolic space, and any complete hyperbolic free manifold can be defined as a quotient of the space by group G, which is a group of isometries acting freely and properly discontinuous. And for this situation, there are very nice theorem proved firstly by Mostov, and next in other versions by Marden and by Prasad, and it can be formulated as the following. Suppose we have 2 complete finite volume hyperbolic n-dimensional manifolds for n at least 3. If there is isomorphism between fundamental groups, that is, it is induced by a unique isometry between these manifolds. Of course, it is not hold in dimension 2, because there is a very nice Teichmüller space theory. Okay, so we have such kind of rigidity, and due to this rigidity, we can consider geometrical invariance as a topological invariance. And among geometrical invariance, we will be interested in volumes. And I would like to calculate concretely. So let me suggest you a 3-dimensional hyperbolic geometry model, and there are many. And one of convenient is the model is the upper half space, and you see there is a quadratic form giving us a metric, and we know a lot about this model. In particular, we know that the full group of orientation per isometry is isomorphic to PSL to C, and action of element of this group can be described in the following form. If you present hyperbolic free space by points coded by a complex number and positive real number. So you see the action described by the formula in the center of the slide. And if we consider just the boundary of our space, absolute of our space, so in the case when t equals 0, we'll get just the standard action of a linear fraction transformation group on extended complex plane. So the way from a boundary to hyperbolic free space, it is quite standard, and geometrically it's looks as you have inversion in a circle, and you extend to inversion is a semi-sphere which is based on this circle. Usually it's called a Poincare extension. It can be done for any dimension, not only for dimension 3. Okay, and now we can think about the group, the discrete torsion free subgroup of P equal to C. We understand the action, and the quotient is a orientable hyperbolic free manifold, since we consider orientation preserving isometries in this case. So we have such a description, and just for intuition, I present a picture of this model. So there is it is clear how it looks lines and how hyperplace looks. And in this point, just remember that what is the ideal polyhedra or ideal vertex? Well, vertex, you call it ideal, it's belongs to the boundary of the space, I mean, or absolute, or it's also called sphere at infinity, or extended complex plane. So it is the ideal vertex. And we say that polyhedra is ideal if all its vertices are ideal vertices. And also in this space, we can calculate volumes. Okay, we can do it directly by the volume form, which comes from distance form. But traditionally and quite useful to calculate volumes in terms of the Lobachevsky function, which is presented here, and also graph with this function is presented here. We take, of course, value from we take values of this function for arguments between 0 and pi over 2 for our calculations. Okay, this is an example how we can apply a Lobachevsky function to find a volume of some ideal polyhedra, exactly tetrahedra. So let me denote by alpha, b, and gamma. Ideal tetrahedron with dihedral angles alpha, beta, gamma incident to positive infinity. It is because of property of ideal property of this tetrahedra. Also, opposite dihedral angles are alpha, beta, and gamma. So this tetrahedra is parameterized by 2 parameters, really, because alpha plus beta plus gamma equal pi, because the basic triangle is just a Euclidean triangle. So this is a picture of our tetrahedron, and the volume formula was presented in such a form by Milner. So it's looks like it's just a sum of free Lobachevsky functions calculated in points alpha, beta, and gamma. It is remarked in the original Milner paper that, of course, this formula can be obtained from original considerations done by Lobachevsky in 19th century. Okay, since we have a family of tetrahedra with 2 parameters, so we can analyze this volume function. It can be easy, not so easy, but it can be shown that maximal volume you will get if all 3 angles alpha, beta, and gamma are pi over 3, and you see this number, this volume. We will use a constant denoted by V3, and you can see expression up to 15 digits. And I just remark again that notations for this tetrahedron is pi over 3, pi over 3, pi over 3. It means that for each vertex, 3 dihedral angle incident to this vertex equal to pi over 3. So all 6 vertex in the tetrahedra equal pi over 3. And relating to the knot theory, it is well known that we can use such a tetrahedra to obtain a figure knot complement. More exactly, we can construct figure knot complement from 2 copies, and arrows show how you identify faces of tetrahedra. So you just take face from one tetrahedra and identify with the face on another tetrahedra with the same labeling of edges. I mean, the same labels showing the same directions. Okay, so it can be glued, and if you want to present it in terms of hyperbolic geometry, if we are interested in fundamental group of this knot complement, and we're interested in faithful discrete representation is a group of isometries of hyperbolic space, and it can be done in the following way. So we have generators A and B for our group, and we just send A to the matrix of the form A1101 and B to the matrix with the intervals 1, 0 minus omega 1, where omega just a complex number presented here. I suppose it was firstly remarked by Robert Riley, and after that many people used this example. This one of the most famous example of hyperbolic knot. A knot which complement the mid-hyperbolic structure. And this kind of group is able to with a ring of integers of some extension of quadratic field. This group were considered by Bianchi in the beginning of 20th century and usually called Bianchi group. And our figure knot group is just index 12 subgroup of Bianchi group. And since we know how to glue knot complement, we know how to find volume. So it's constructed from 2 ideal regular tetrahedra, so volume just 2 times volume of ideal tetrahedra. So we use the same constant V3 as the previous slide. Of course, we can use this way. I mean, we can try to understand which kind of manifold or which kind of link complements you can construct from ideal regular tetrahedra. And we studied this equation with Evgeny Fominih, Stars Karafalidis, Matthias Björner, and Volodya Tarkaev. And we tabulated all 11,550 orientable manifolds, which can be obtained from at most 25 copies of ideal regular tetrahedra. And also we considered non-orientable manifolds. The number of non-orientable is bigger, and we tabulated all 25,194 non-orientable guys, which can be obtained from at most 21 copies of such tetrahedra. And on this way, we passed 2 steps. Firstly, we generated manifolds. We described manifolds in terms of triangulation. So firstly, we suggested some gluing tetrahedra to obtain manifolds. So we check that you obtain manifolds, and automatically you get hyperbolic manifolds because you glued manifold from hyperbolic tetrahedra by hyperbolic isometries. And using this approach, it was possible we obtained the same manifolds. We just have different triangulations. So it was necessary to distinguish manifolds and check if different triangulations give different manifolds, or understand if they give the same. And it was a little bit difficult because you cannot use the volumes, because if you fix number of tetrahedra, for example, 25, so all these manifolds have the same volume, 25 times V3. So you need to use another ideas, and we did it. And this paper is published in the Journal of Experimental Mathematics, but also you can find it in arXiv. In arXiv version, there are a lot of attached files which contains information about all these manifolds. There are coding, there are volumes, there are properties, and so on. And these manifolds, and of course, we are interested in other some linked complements, and which exactly. So just to give you an example, for the case when you consider 10 copies of ideal regular tetrahedra, and among a lot of manifolds we constructed, there are also linked complements, and some of them are presented here. There are 8 linked complements, such that there are 8 links, such that there are complements can be decomposed in 10 ideal regular tetrahedra. And you see some of them are alternating, non-alternating. They have different number of crossings, but all of them belong to this family. And I started to talk about hyperbolic structures, and I would like to recall you very famous result, which was proved by Thurston in 82. But now we can consider it is just a corollary from the more general generalization theorem. We can consider as a particular case of generalization theorem. It's related to the case of nodes in three-dimensional sphere. So Thurston proved that node complement has one of model geometry structures with exactly 8 Thurston geometries. If and only if a node is not a satellite. And I recall you that what means a satellite? Suppose a node is placed inside a solid torus, which suppose it's called V, and V itself is not in the space. Then the key is called a satellite node. So firstly, it's not a satellite node, and node complement has a hyperbolic structure if and only if, in addition, node is not a torus node. Yeah, just recall the torus node is a simple closed curve sitting on a standardly embedded torus. And we have such a theorem, and I would like to mention that really there are not so many non-hyperbolic nodes if you tabulate nodes of small order. And I would like to refer to the nice paper by Jim Host, more than this is played in Jeffrey Weeks. They tabulated 1,700,000 nodes, which can be obtained from 60 have diagrams with mostly 16 crossings. And in the paper, they remarked that there are only among these 1,000,000.7 nodes, only 32 are not hyperbolic, and among them just 12 torus nodes and 20 satellites. And satellites also described, and I present the next slide. So these satellite nodes can be presented uniformly in the following way. So we take just not a scheme presented here, and a shaded disk, and just you need to put tangle drawn here in the shaded disk, this tangle and interval in yours, and these 20 guys are satellite nodes according to the definition. So all other are hyperbolic, and since they're hyperbolic, we can ask about volume. So we can calculate volume at least numerically. And there is very nice conjecture, which is usually called it volume conjecture or Kashaev conjecture, as Kashaev-Murakami volume conjecture. The conjecture says the following. Suppose you have hyperbolic link, and just consider nth Color-Jones polynomial. Yeah, I just recall that classic original Jones polynomial correspond to the case n equal 2. And let's consider the limit of special values of this color Jones polynomial. So we just calculate each polynomial with number n in some special point, which is root of unity, presented here. And we have sequence of numbers. I consider limit. And the conjecture says that this limit is just volume of the link complement. Originally, this conjecture was formulated by Renat Kashaev, and he used kind of quantum algorithm. It was in 97. And later, Hitoshi Murakami and Jun Murakami observed that the Kashaev invariant can be expressed via the colored Jones polynomial, and this expression presented just in the formula. So it's just special values of colored Jones polynomial. And I would like to recommend, I hope you will enjoy reading the book written by Murakami and Ikota. It's called Volume Conjecture for Knot. It's published in 5 years ago by Springer. So there is very nice relation, conjectured relation between Jones generation of the Jones polynomial and hyperbolic structure on the knot complement. This conjecture proved for few examples. You can find in the literature very easy. And now I would like to tell you about some other volume conjecture related to Turaev-Firo invariance. And I think I need to recall what is a Turaev-Firo invariant. It's a little bit boring, but I need to do. So let's first we start with some quantum numbers and quantum factorial ideas. There are different descriptions of Turaev-Firo invariance. I will follow the description presented in the paper written by Chen and Yang. Also, you can find in original Turaev-Firo paper, also in Matveyev book, and there are many different descriptions, a little bit different, but giving the same result. So let us start with some number R, which is at least 3, and consider non-negative half integers from 0 to R minus 2 divided by 2. So this set of half integers denoted, which we denote by IR, and we'll think about elements of this set as the colors. So our colors are half integers. And let us consider the root of unity, Q, such that Q square is the primitive root of order R. And after that, we will work with quantum integers. So for positive integer n, quantum integer means the expression in terms of Q is presented here. And quantum factorial, just a product of such quantum integers. So our numbers, our integers, our factorials are always quantum from this point. And let us think about colors, which are half integers. And we consider the triple of colors. This triple will say to be admissible if we have inequalities. So I plus G is at least K, and so on. And also we require that I plus G plus K is an integer, and some of these integers is related to R, so this is at most R minus 2. So this triple of admissible integers. Okay, now we go to tetrahedron. So now let us take 6 colors. So I, J, K, L, M, N. There are again still half integers in the previous sense. And we will say this 6 tuple is admissible if every 4 triples I, J, K, J, L, N, I, M, N, KLM are admissible. You can think about this situation as colors correspond to edges of tetrahedra as presented here. So these four triples just correspond to faces of the tetrahedra. Also, we denote epsilon, just some of these colors. And now we'll think about tetrahedra, and for admissible triple ABC, denote by TS, just sum of ABC, and they define delta, just square root of fractional expression presented in the slide. So we have four TI, which are given for admissible triples as before. They correspond to faces of tetrahedra. Also, we can consider sets of four edges. So in the picture you see we can consider four edges, for example, corresponding to quadrilateral drawn inside the tetrahedron. So IJLM and Q1 is just sum of colors corresponding to this quadrilateral. And you can consider another two. So Q2 and Q3 are corresponding sum of numbers. So it's related to normal, the parts of normal surfaces embedded to triangles and to tetrahedra. So I just want to remark that this is only combinatorial construction. Yes, so you have admissible colors and you have tetrahedra and correspond some numbers to collections of faces and quadrilaterals embedded in tetrahedra. And our next step will correspond to 6G symbol. It is not a matrix, it's just a notation for 6 numbers. So we take some by Z from maximal TG to minimal QG, and such expression in terms of quantum factorials. After that, we take the product. All these parameters are defined in the previous slide. So to each tetrahedra, we correspond such a 6J symbol. And since we use its symmetry in definition of T and Q, we have the following property. 6J, we can permute our symbols and the results will be the same. So 6J symbols can be coded by our tetrahedra. So we take symbols corresponding to H incident one face, and this give us the first line, and opposite H give the second line. After all this permutation, we describe 6G symbol related to tetrahedron. Okay, and after that we also define the weight, which is correspond to the color. And now suppose we have triangulation of our free manifold. So T is a triangulation of a manifold, and for each edge we take a color, and we take we consider admissible coloring of edges, and after that we just correspond to our triangulation to each tetrahedra from our triangulation corresponds to the 6J symbol, which colors obtained from global coloring of tetrahedra of triangulation. And after that, we construct a tri-Ferro invariant of a manifold. So you see, we consider products of weights corresponding to tetrahedra After that, products of coloring corresponding to ages. You take a sum of all possible, all admissible colorings, and you have also a multiply which give us some weights in degree, sum of some weight squares in degree minus the number of vertices. So this very nice invariant, use it in theory of free manifolds. And for example, is a paper that I mentioned before about construction tetrahedra with Egorov and Andrei. We initially distinguished manifolds by using Toraya-Ferro invariant. It's difficult to calculate this invariant by hand, but computer, you can do it. And why I started to talk about Toraya-Ferro invariant? Because of the following conjecture, which is again a kind of volume conjecture posted by Cheng and Yang 5 years ago. So the conjecture is the following. Suppose we have a manifold which is hyperbolic, three-dimensional. It can be closed, or it can be viscous, or it can be compact with a geodesic boundary. So all these possible cases admitted. And at the beginning of construction Toraya-Ferro invariant, there is a parameter R, the first integer parameter from which we started. And we have a family of Toraya-Ferro invariants parameterized by this R. And each Toraya-Ferro invariant gives us some number. It's boring to calculate, but finally we get a number. And consider log of these numbers and consider limit. So we consider log divided by R, multiply by 2 pi, and consider the limit. And conjecture is you obtain a volume of a manifold. So in the Kashayev case, Kashayev-Murakami case, it was Haller-Jones polynomial, but now it is a different construction related to Toraya-Ferro. And in particular, in the case of link, there is conjecture by the same authors. So if you have a link, if you consider R which runs over all odd integers, so the conjecture that the same left part did, as before, give you volume of the link complement. Not exactly give you Gromov norm, simplicial volume of the link multiplied by constant V3. This is for the case if you have link which admit Jacob Sharon-Johansson decomposition. So some paths will be geometric paths and some will be ciphered. And for hyperbolic path, it give you hyperbolic volume, and for other give you 0. So if you think only about hyperbolic link, so the right part just the volume of link complement. And this conjecture was proved in some cases by Dutchery, Kofogiani, and Young. More exactly, they proved it for the figure 8 knot and for the Brahmin rings. So you see the theorem. So if R is odd, so this left part related to Toraya-Ferro invariant, it can be expressed in terms of Haller-Jones polynomial of this link, and finally give you the volume. This is for manifold, for cusped, closet, and closet with a geodesic boundary. And for the case of links, it was proved by proved for figure 8 knot in Brahmin rings. And I would like to present you some calculations done by Cheng and Yang in particular cases. Just want to illustrate for simple knots. If you have the figure 8 knot, and you consider complement. So the volume of the complement we know is approximately 2.0298, just only 4 first digits. And as we observed before, the figure-eight-node complement can be constructed from two ideal regular tetrahedra, and this tetrahedra presented in the picture, and also they're indicated the Grunov edges. So there are two classes of equivalent edges, so 6 edges with label A and 6 edges with label B. So triangulation have two tetrahedra, and for these A and B edges, we consider coloring, so admissible coloring, and you see there are vertices type which give us triples AAB and BBA. So we need to consider admissible coloring for these edges, and to arrive a row invariant for these manifolds looks just the sum of all colorings. There are ways VA and VB for two type of edges, and also two 6J symbols for one tetrahedra and for another one. So Chen and Yang calculated this case and observed that their conjecture numerically hold. This case of figure-eight node, and also they consider the case of 5-2 node. It is also very normal that a complement of this node can be obtained from free tetrahedra. Now they are not regular, but still ideal. And since there are free tetrahedra, there will be free 6J symbols, and they observed admissible triples. For formula, just for trifer invariant, just sum of all colorings. Also, they check it that the left part of the conjecture give us the same as we expect, so it gives the volume of a not complement. They represented just initial, okay. And now I want to discuss something similar to previous conjecture, also formulated by people. This conjecture, which you now call it maximum volume conjecture, is related to polyhedra, or you can think about graph, which is a skeleton of polyhedra. So let's consider graph in the three-dimensional sphere, and suppose it is free connected plane graph. So it's graph which can be arise as one skeleton of polyhedra. So it's plane, else it's free connected. It means connected, edge connected. And their conjecture formulated by Konstantin Garitao van der Wien. If they define it, TV now is not derived row invariant, which was for manifolds, but they introduced some invariant for graphs. It's based on Yokota polynomial for special graphs, but now just plain graph. But they also still call it a Torah-Firo. So this TVR is analog of Torah-Firo invariant, but for plain graphs. It's not easy to define. I mean, maybe 10 more minutes to define it. So I skip just important is some analog of Torah-Firo. So they conjecture that if you consider the same kind of construction, so you take invariant for plane graph and calculate some special point, you have sequence of numbers. After that, you take logarithm, you divide by r, and you multiplied by pi, and consider the limit. So the conjecture, so in this case, you'll get a supreme of volumes of hyperbolic polyhedra for which our graph is one skeleton. So it's means that you fix it, combinatorial type of your polyhedra, and you consider that all possible polyhedra with such skeletons, or for example, all tetrahedra, all cubes, and you consider supreme of volume. So the conjecture that the limit is exactly the supreme. And of course, they consider some families of graphs and prove this conjecture for some cases. And what I'm interested in now, I'm interested in the right part of this conjecture. So what is the supreme of volume? And last April, it was published very nice paper by Giovanni Belletti. It was published in Transactions of American Mathematical Society. So he studied the right part, and he proved the following. So the right part, the supreme, is just the volume of polyhedra, which can be obtained as the truncation of rectification of graph gamma. So rectification is a term introduced by Belletti. And it's held for all kinds of vertices. So now we admit polyhedra with finite vertices, ideal vertices, or ultra-ideal vertices. So we just need a combinatorics. This is a very general case. So for generalized hyperbolic polyhedra. So let me give you some idea. So suppose you have tetrahedron in projective model. So you consider the model of hyperbolic geometry in the ball, and vertex can be finite. So inside in the ball, maybe ideal or the boundary of the ball, or it can be outside. In the case of outside, you consider the polar plane and truncate by this plane. So in the case of extra ideal vertex, you truncate, and you have all such type of vertices, finite, ideal, or truncated. I mean, in the case of truncated, you just consider the polar plane. And simple example is the tetrahedron. So you can think about this generalization as the following. So you have usual simplex, or simplex is truncated ultra ideal vertices. Of course, in this hyperbolic space, it's already not simplex, but we'll think about this guy as a simplex. And so you can truncate, and you can truncate up to the situation when you meet h of the simplex only in one point. I mean, so you do truncation until this point, and from getting this rectification, you obtain a polyhedra already in hyperbolic space, as presented in the picture below. So you started from tetrahedra, did truncated, and finally obtained an octahedron. And vertices of this octahedron belong to the edges of tetrahedron, so they belong to the boundary of hyperbolic space. So it's obtained ideal octahedron. And moreover, all lateral angles now equal pi over 2. And the following graph presents the situation of tetrahedra. So if angle is about arccosine of 1 over 3, you have situation near the Euclidean one. After that, you go to pi over 3, which correspond to ideal regular case. For smaller lateral angles, you have still ideal or still maybe partially truncated or partially ideal vertices, and volume increase. And for zero case, I mean all laterals zero, so you obtain a volume of octahedron, so 3.66. So this is a picture for tetrahedra in general case, generalized tetrahedra. It's possible to have finite vertices, ideal vertices, or ultra ideal vertices. So we see there is a duality between the polyhedra and ideal regular polyhedra, ideal rectangular polyhedra. For example, if you have a pyramid, so corresponding polyhedra is antiprism, like presented here. This relation can be obtained in terms of graphs. So one is medial to another, or one is a graph of chessboard coloring of another. And the family of ideal rectangular polyhedra is very interesting, but we have a very nice combinatorial description. So foreign combinatorial polyhedra admits the realization of ideal rectangles if and only if it has no non-trivial vertices and don't have free circuits. Also, you can check by early form of polyhedra that such a polyhedra always has at least 8 triangular faces. So the smallest one is a polyhedron, and we have more information. We can estimate volume in terms of the number of faces. First such estimate was done by Christopher Atkinson, and he has a lower and upper bound. After that, together with Andrei Egorov, he improved the upper bound, and the set of volumes is presented on this picture. You have a low bound from Atkinson and upper bound from our paper, and points between these two lines, just volumes of the ideal rectangle hyperbolic polyhedra, which up to 21 vertices, so 23 faces. So this is all possible volumes. There are many polyhedra with the same volumes in this case, and we have lower and upper bound. And just recently we improved the upper bound. So if we start from 27 faces, so jointly with Stepan Alexandrov, Nikolai Bogachev, and Andrei Egorov, we obtained a little bit better upper bound. So it's presented here. And F is still the number of faces of ideal rectangular polyhedra, and V8 is just a constant. I presented here. And using Belletti, a result about right path in the maximum volume conjecture, we can obtain the upper bound for arbitrary polyhedra, since we know volumes of ideal rectangle. And this is our joint result with Andrei Egorov. This is in progress, and we obtain for arbitrary polyhedra with edges, we obtain such linear bound. This for volume of generalized hyperbolic polyhedra with any type of vertices, I mean, with the finite, ideal, or ultra ideal. And in later talk by Egorov, he will tell more about this result, I hope. Thank you very much for your attention. It seems almost in time.
Thank you, Andrei, for the wonderful talk. Are there any questions or comments? Okay, so Andrei, I have a rather naive question. So I think there is a definition of zones polynomial for virtual knots. And if you view them in thickened surfaces, is there some sort of volume conjecture or something like that?
There are some calculations of volume of complements of virtual knots. Yes, it was done by Colin Adams with his students. But I'm not sure what we need to consider in the left. But I mean, we can think about to write your version of foreign conjecture, because we consider three-dimensional manifold, which is not complement in handle body. So in this sense, yes, but I don't think that somebody checked it.
Yeah, but they use the Turai-Vera invariant. So
Yeah, using Turai-Vera, yes.
I was just wondering whether there is some colored Jones analog, and then you can use something at appropriate evaluation.
It's a good question. Yeah. Yeah, but I think open.
Thank you. So, okay, so let us thank the speaker once again for wonderful talk.